Good evening, everyone. In this opportunity, I will present our research paper entitled Best Fit Heuristic Algorithm for Multi-Stack Rectangular Packing Problem of NC Router Machine. This paper was authored by me, Irfan Shah Ali, Wisnu Aribowo, and Sukoyo. And all of the authors are from Department of Industrial Engineering, Institut Teknologi Bandung. This research is motivated by a nesting problem in a CNC router machine in a metalworking company, where efficient cutting patterns are desired in order to minimize material usage. Nesting is one of the important processes in the whole production processes. It can minimize so much cost if it is done appropriately and efficiently. In this research case, there are several features and characteristics that have not been considered and aligned in the existing nesting process with the real condition, which make the nesting result is not effective and efficient. First is the size of metal sheets used in the shop are varies, which means the width and length of each sheet may differ. This condition has not yet been considered in the existing process yet, which often makes the sheet selection is inefficient. The cutting patterns formed will not be compact and leave so much unused space. Second, the CNC router machine can cut several stacked sheets at a time on the condition that the sheets have the exact same cutting patterns. This feature has not been considered and applied in the existing shop. Applying this feature will save much setup and cutting time. Third, the cutting patterns formed by the current process tend to be scattered and not compact, while on the contrary, the ideal condition is that the parts allocation or cutting patterns must be designed compactly to minimize the unused space material that will be scrapped if there are any. The unused space can be used again for the next cutting process if the leftover size is large enough, at least as big as the smallest length or width of the parts. Each characteristics mentioned before becomes the fundamental in developing the proposed algorithm in this research. And we propose an heuristic algorithm that consider those characteristics. The proposed algorithm called best fit heuristic algorithm with variable size sheets, usable leftover and stack sheets consideration. The proposed algorithm was developed based on the BFHA in Chen et al. 2019 for the heuristic packing strategy structure, which is then adapted to specific characteristic as inspired by Liu et al. 2011, Andrade et al. 2014, Sumeta Piwat et al. 2020, and Aribowo et al. 2021. The following is an example of one of the proposed algorithm stages in forming solution. Suppose iteration with values g equal 3 and d equal 0. This is the list of the parts and this is the list of the sheets. The first is the initiation process. First, the amount of SUL or space for usable leftover is determined. It is known that part 2 has the shortest side, which is the width with value of 2. Then SUL size is determined as 2. Then the sorting process is done by descending order by area. After that, we observe if there are any priority parts. It is done by tentatively try pack any parts into each sheet type available. It is known that in this case, there are priority parts, which is part 3, or a part that could only be packed into one specific type of sheet and in a specific orientation. So the largest or most fit sheet will be used. Then the priority part and part RG and part RJ or part 1 are issued in the list to be packed and form the initial layout. The priority part will always be packed first. Then the RJ part, then the other parts in the list will be considered after. Before priority parts and RJ parts are packed, other parts are not considered. If the RJ part cannot be packed in the same sheet as the priority part, the RJ part will be packed and form the initial layout on the next sheet. Even though there are parts in the list that are able to be packed on the same sheet as the priority part, this is not done for the purpose of diversifying solutions. After that, the packing process is stopped, and the process of considering usable leftover and stack sheet is started. Usable leftover allocation is tentatively and iteratively considered on the right, top, and top right of the sheet. If the minimum amount of SUL overlap a packed part, like this, then the allocation of SUL is not carried out, because after all, packed parts in sheet is better than SUL allocation. Next, a search for multiply factor values that can meet the demand of part 3 type was carried out by identifying each part packed in the sheet. It is known that there is only one part 3 packed in the sheet, and the part 3 demand is 3 pieces. So we can multiply and make 3 exact same cutting patterns by multiply the sheets by 3. The 3 value that was obtained can be a multiplier factor, which also becomes the number of stacks for this batch. So for batch M1, a cutting pattern is formed with 3 stacks of sheets. The search for the multiplier will also depend on the number of available sheets type used. Then after that, the type 1 part, which became the previous RJ, is packed on the next sheet. Sheet selection is done with condition 2, when the priority part doesn't exist anymore and the amount of material is greater than 20%. Then a large sheet is used. The following step is an example of how the best fit heuristic algorithm from Chen et al. 2019 is done. Picking a type 1 part will form the initial layout and generate an angle occupying placement or AOP as a space for packing parts in the list. Then each part is tentatively packed on each AOP sequentially in the order of horizontal vertical orientation. This is angle 1, this is angle 2. Angle 1 and angle 2, it is basically considering as bottom left angle available in the sheet. From each AOP, the number of angles occupied by the part will be scored, or in this case, the term is fit degree, as the value that determines which angle or AOP will be chosen to pack the part. It is known that the AOP of part 1 at the bottom is greater with fit degree of 4. Then this AOP of part 1 is chosen to pack part 1. The process of calculating the fit degree for each AOP resulting from the packaging of part continues until the sheet is completely filled. Next, considering the UL and the US. Next, considering the usable leftover and stack sheet. It is known that by forming M2, the number of parts in the list remaining is less than 20%. So the smallest sheet size is used. Because part 1 has not been packed completely, then part 1 returns to RJ because of the order rules. Packing process considering UL and SS are done again. So we obtain M3 or batch 3 with one stack sheets, but only one stack sheets. It is known that by forming M3 in the previous process, the number of remaining parts in the list is less than 20%. So the smallest sheet size is used. Part 2 is packed as RJ in forming the initial layout, and because there are no parts that need to be packed again, the usable leftover stack sheets consideration process is carried out. After that, it is known that all of the parts are packed, nothing should be packed again, and one solution is formed. Then the objective function is calculated. For the whole algorithm process, the objective function that we obtain in every iteration will be compared with the previous iteration to choose the best objective function value. In this case, is minimum. In order to illustrate the packing process flow and to verify the algorithm, we use the same case, same objective, and same small hypothetical data that are also used in the optimal model of previous research by Aribowo et al. 2021. Here's the data. However, it should be noted that there are two differences between the proposed algorithm and the optimal model. First, the proposed algorithm considers 90-degree rotation, while the optimal model does not. The proposed algorithm takes into account usable leftover that is formed on the top side as well as on the right side of the sheets, while the optimal model only allows usable leftover on the right side. Consequently, for equivalent comparison analysis purposes, we make a temporary adjustment in the proposed algorithm by limiting the allocation of usable leftover on the right side only and by avoiding rotation. Here are the results by using more or less the same stages or steps as the demonstration before, of course, with the equality adjustment. The proposed algorithm obtained a 522 objective function value that is close to the one that optimal model obtained, which is 472. So we conclude that the proposed algorithm has succeeded in solving the multi-stack rectangular packing problem. The numerical example shows that the algorithm can generate a pretty good solution with 10.06% difference compared to the optimal solution. And for further research, we also plan to further develop the proposed algorithm to be able to solve various part shapes and develop a meta-heuristic approach to improve the algorithm searching ability. And that concludes our presentation. Sorry for all the flaws and shortcomings, and thank you for your attention.